Every AI headline still depends on something physical: power into a building, heat out of a rack, wafers through a fab schedule. When capacity tightens, the constraint is rarely a missing app feature. Today, we follow the engineering bottleneck behind the software story. The biggest threat to scaling artificial intelligence isn't a lack of clever code or better algorithms. It is a very real physical danger lurking in your local power grid: voltage sags that can melt down entire data centers before they even finish training a single model. For years, engineers have been solving this problem the hard way. They built massive backup systems and oversized their electrical infrastructure to handle worst-case scenarios. But there is a new solution emerging from a collaboration between Microsoft, OpenAI, and NVIDIA that changes the game entirely. It is called restartable sequences, and it represents a fundamental shift in how we think about hardware limits. This isn't just another software patch for logic failures or workflow adjustments. This is a hardware-level intervention designed to let data centers survive electrical instability without melting down. To understand why this matters, you have to look at the strange behavior of modern GPU clusters during training. When you run massive large language models, the GPUs do not draw power smoothly like an old incandescent light bulb would. Instead, they operate in a bulk synchronous paradigm where thousands of chips alternate violently between intense computation and idle communication phases. This creates massive power swings that can spike by tens or even hundreds of megawatts in a fraction of a second. These rapid fluctuations are not random noise. They have the potential to harmonize with resonant frequencies already present on the electrical grid, creating feedback loops that risk physical damage to turbines and transmission lines far away from the data center itself. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The problem becomes acute during these micro-interruptions known as voltage sags. Standard uninterruptible power supply systems are designed to bridge gaps lasting seconds or minutes when a line actually goes down completely. They cannot react fast enough for the specific 10 to 100 millisecond dips caused by the oscillation between total thermal design power computation and idle communication states. In these tiny windows, standard infrastructure sees nothing but chaos. If the voltage drops even slightly during a critical moment of high load, the system can trigger a cascade failure that forces an immediate shutdown to prevent hardware from melting or burning out due to thermal runaway. This is where restartable sequences steps in as a radical departure from traditional engineering approaches. Instead of asking the grid to be stronger or building bigger batteries, this approach modifies how the workload itself behaves at the silicon level. The core innovation allows the GPU cores to pause and restart specific sequences instantly if they detect an instability event that would otherwise cause a crash. By decoupling the training workload's power profile from the strict stability limits of the grid, we can allow data centers to scale their GPU counts far beyond what was previously possible without risking physical destruction. Think of it as changing the rhythm of the music rather than trying to reinforce the floorboards so they never shake again. The engineering trade-off shifts dramatically here. Previously, if you wanted to add more GPUs, you had to oversize your power infrastructure significantly to handle those worst-case spikes in demand, which meant installing massive, expensive, redundant power rails that sat idle most of the time. Now, with dynamic workload sequencing smoothing out the aggregate power curve, we can reduce the need for such extreme overbuilding. The system becomes resilient by design rather than brute force. This shift was validated through rigorous testing using real hardware and Microsoft's Cloud Power Simulator. The results showed a clear path to grid integrity that logic-based workflow tools simply cannot address. Those other solutions focus on code generation errors or verbosity, which are irrelevant when the threat is electrical infrastructure stability. Restartable sequences targets the specific frequency of instability caused by the bulk synchronous paradigm and dampens it effectively. It prevents the physical melting of power delivery networks that standard UPS systems have historically failed to mitigate within those critical 10 to 100 millisecond windows. The implications for scaling are profound. We are no longer constrained by the point where voltage sag-induced thermal runaway forces a shutdown. By altering these physical limits, we unlock an economic model change as well. The cost of adding capacity drops because you do not need to build redundant power rails that are 3 times larger than necessary just in case. This allows hyperscalers and cloud providers to expand their AI capabilities at a pace previously thought impossible given the constraints of existing electrical grids. However, this solution is not without its complexities. It relies on specific hardware modifications from GPU vendors like NVIDIA and cooperation across the supply chain for implementation. While real-world adoption timelines may vary depending on how quickly these changes can be retrofitted into diverse grid infrastructures worldwide, the proof of concept demonstrates that the path forward lies in this deep integration of software scheduling with physical layer constraints. The gap between AI hype and physical reality is closing not by ignoring the laws of physics, but by engineering around them with unprecedented precision. We are moving past an era where we simply hope our power lines can handle a new cluster of chips. We are entering a time where the code itself understands the grid's limitations and adjusts its rhythm to keep everything safe. This is the genuine technology story behind the headlines, hardware, manufacturing, and infrastructure engineering working in concert to make the impossible possible. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.